Okay, in today's video, we are going to go over a problem involving orbital period. We're going to actually do two things in this video. One is we're going to derive the equation for orbital period, and the second thing we're going to do is we are going to do a couple examples for calculating the orbital period of an object. So let's get started. So let's just say we have this object M2. It is orbiting around this central mass M1, and we're going to determine the orbital period of M2 from its known height above the Earth's surface, or from the surface of the central object. So we have M2, it's a mass, maybe a satellite or a moon, and it's orbiting the central mass, which is M1, and we're going to determine the orbital period, the time it takes for that M2 to go around one time. Okay, now this is based on the forces, and we know that we have a force that's acting on M2 from M1, and that force points right to the center of M1. So this arrow represents the force on M2 from M1. Now we know also that we have an equal and opposite, a force that is equal in magnitude but opposite in direction, a force that's acting on M1, the central mass. This is the force on M1 from M2. And we know that these two forces are equal in magnitude but opposite in direction. Now when we have an object that's going on a circular path, okay, or a curved path, then the force that keeps that object on that path, so the force on 2 from 1 is going to be called the centripetal force. Okay, that's the force that keeps an object moving on a curved path. This force we're just going to designate the gravitational force, Fg. Okay, and we know now, as we said before, that these two forces are equal in magnitude, but opposite in direction. And we're going to use that idea, which we're going to do now, is to derive the equation for the orbital period. Okay, we're going to start with M2, the force acting on M2, which we said is the centripetal force, and we get that force from Newton's second law, which is F equals ma. But when an object is moving on a curved path, then the acceleration of that object is given as acceleration is equal to v squared, the velocity of the object squared, divided by the radius of the object's orbit. Okay? You have to remember that the radius is from the center of the center mass out to the object. It's not just the height of the object above the surface of the central mass. Okay? This radius is from the center of mass of the central object. Okay, we can put these two equations together, and we get that the centripetal force, I put Fc now for centripetal force, is equal to the mass of M2 times the velocity squared divided by the radius. Okay, so that's the equation for the centripetal force. And for the gravitational force, we're simply going to use Newton's law of universal gravitation, or Newton's universal law of gravitation. And we are going to say that we know that is the force of gravity is equal to g, which is a constant, times m1 times m2 divided by the radius squared. Okay, this is often called an inverse square law because it's the radius squared. All right, and the force is inversely proportional to the square of the radius between the two objects. Okay, now, as we said a couple times, we know these two forces are equal in magnitude but opposite in direction. So that means we can set these two equations equal to each other. Fc is equal to Fg. That means that m2 v squared divided by r is equal to g m1 m2 divided by r squared. All right. Now we're going to simplify this equation, and we know we have an m2 on both sides, so we can cancel those m2s. That's the mass of that orbiting object. And we can see we have a radius here and a radius squared here, so we have one radius here and two radii here, so we can cancel this r and one of those two. And now you can see that we are left with v squared is equal to g times m1 divided by r. Now we want to calculate the orbital period, and you notice here we don't have a p, we don't have a t here or something a p, but the orbital period is designated with a t for time. There's no time in this equation, but we're going to bring a time in here because we know that the velocity is equal to the distance divided by the time. Okay, so over here we're going to say that velocity is equal to distance divided by time. This object is going on a circular path, so that distance is the circumference of the circle, and the equation for the circumference of the circle is 2 pi r. So this distance is calculated as 2 pi r, and that is divided by the time. It's the distance divided by time. Now I switch this from a lowercase t to an uppercase t because orbital period, or the period of an object, is usually given as a capital, or designated with a capital t. All right, I'm going to take this term here and plug it into here for v squared, but it's v squared, so I have to square all those terms. I have to square the 2, which gives me 4, pi squared r squared divided by t squared, and that is equal to gm1 divided by r. Okay, now we're getting there. This is the t we're going to solve for, so we're going to bring this equation up here now. I'm going to solve for t. I'm going to cross multiply across this way and across this way, and if I do that, I get 4 pi squared r cubed, because here's an r squared and an r, that gives me r cubed, is equal to t squared, this is the period squared, times gm1, and this is gm1. Cross multiplication, solve for t. I'm going to divide simply the equation on the left hand, both sides of the equation, by gm1, or g times m1, and that gives me that the square of the period squared is equal to 4 times pi squared times r cubed divided by gm1. But I don't want to know the period squared, I want to know the period. So I'm now going to take the square root of both sides, and that gives me that t. This is the period is equal to the square root of 4 pi squared r cubed divided by g times m. That is the equation we use to calculate the orbital period of an object. Now I want to point out once again, if you look in this equation, there's really kind of only one variable, and the variable in this equation is the height, or the radius the object is, the radius or the height the object is above the surface of the central mass. You'll notice that m2, which is the mass of the object, is not in this equation. That means that the orbital period is not dependent upon the mass of the orbiting object. It's really just dependent on, this is a 4 constant, so to speak. This is pi, it's also squared, constant. The radius, of course, and this is a constant, and then this is the m1 is the mass of the central object. But usually we have kind of a fixed central mass, and we talk about the period based on the radius, the distance the object is away. So really I kind of think of it that the only real variable in this equation is the radius. All right, that means that if I take another object and put it in the same orbit, and let's say I say it's 2 times, the mass is twice that of m2, it will have the same orbital period. The orbital period will not be different because the mass does not affect the orbital period, the time it takes to go around once. Okay, so there's the equation. Now we're going to do a simple example with a GPS satellite. A lot of GPS satellites have this height above the Earth's surface, 20,181 kilometers. And we're going to use our equation right here, and we're simply going to plug the values in, that the period is equal to the square root of 4 pi squared, and then it's the radius cubed. Now we have to remember that the radius is the distance from the center of mass of the central object to the center of mass of the orbiting object. And in this case, for Earth, okay, we're talking about Earth, this would be Earth, this would be a GPS satellite. That would mean that the radius is really equal to the height above the Earth's surface plus the radius of the Earth. Well, we said the height is 20,181 kilometers. The radius of the Earth is 6,371 kilometers. So I add those together and convert to meters. If I add these two together, I get 26,552. It has to be in meters. The radius has to be in meters because my constant g has units of meters in it. So this is times 10 to the third meters cubed. Then I just divide by the mass, that's my gravitational constant. 6.67 times 10 to the minus 11 Newton meter squared kilogram squared. So you have meters here, so this has to be in meters. And then the mass has to be in kilograms because I have kilograms here. And this is the mass of the Earth because this is the center object, which we're saying in this case is the Earth. I do all that, get that math, and I get that the period is 43,058 seconds. A little more convenient might be 717.6 minutes or 12 hours. So an object, any object at this height, regardless of its mass, will have an orbital period of 12 hours. Okay, that's the orbital period. Now I think we'll just show you quickly how to calculate the velocity of the object, the orbital velocity. It's pretty easy to do. We're going to go back to our velocity equation, which is distance divided by time. We said once again that the distance is pi r squared, not pi r squared, that's the radius, then that's the area. The distance is 2 pi r, that's the equation for the circumference of the circle. We know the radius. And then we're going to plug those values in. Once again, we have our radius from the center of the Earth. the height plus the radius of the Earth, and we divide that by that period, which we count 12 hours. And if you do that, you get that that object at that height will be moving at 13,985 kilometers per hour, or 3.88 kilometers per second. Okay, I think that's everything we were going to do. We derived the equation, first of all, from the equation of the centripetal force and the gravitational equation. And then we did an example to calculate the orbital radius, the orbital period, and then we got the orbital velocity for that height. Okay, so there you go. Thank you very much for watching. Please